Dustin Lang, who will talk about the medium band imaging survey for future astronomy and cosmology.
Okay, thank you, everyone. I guess we've heard a lot about these medium bands so far, so I just wanted to orient you a little bit: U band, G band, R band. The 5 bands we're talking about here are within the G band. The leftmost one just meets up with the calcium H&K filter that Nicolas was talking about for pristine. So these are excellent for doing this selection of. These are excellent for, as Christoph said, selecting high redshifts 2 and above, like 2 up to 3.5-ish, Lyman alpha emitting galaxies and Lyman break galaxies, essentially because you see either the Lyman alpha line or the break shift between those filters. But by the same token, they're also great for doing photoz's for low redshift galaxies up to about redshift of 0.4, because you see the 4,000 angstrom break move between those filters. So so they really give you a lot of leverage on multiple kinds of galaxy populations as well as stars. Okay, so we have a pilot survey, a 90-night pilot survey running on dark energy camera right now in Chile. We're observing tonight. And we've built all of these 5 filters and taken deep data on Cosmos and XMM-LLS. We should release those data very soon to make them available for people to look at and experiment with. As with our previous DESI imaging surveys, these are fully public surveys, so there's no proprietary time, and we're aiming to do frequent full data releases. And we've also proposed a 260-night or 263-night extension to do by the 5,000 square degrees we want to get, or maybe 3,000. Okay, so, and then a coordinated effort is also happening using hypersuprime cam. And this is led by Hiranao Miyatake and colleagues at Nagoya. And we've coordinated with them to have exactly the same filter band passes. So their filters are a bit of a peculiar design where they have 4 filters at once in different quadrants in the focal plane. And so the first 4 filters have been built and are going to be delivered, and they'll be applying for time this autumn. So, and the goal with that would be to observe a portion of the HSC Strategic Survey Program footprint, so the equatorial part of the HSC footprint. Okay, so the footprint we're aiming for DESI 2 is this 5,000 square degree equatorial stripe. So that's shown in gray here, and the LSST limits are shown as the green lines. We'll probably move around the footprint to fully overlap the LSST. The Euclid ecliptic exclusion zone is in the red, so we have about 50% overlap with Euclid, if I understand correctly. And I guess the depth we're shooting for in each of these filters is 25th meg. And then I guess the big number is sort of here of the time prediction that we'll need. So using 10-hour nights, we predict roughly about 100 nights for these filters with CFHT. So with the 5-hour per night math that you seem to use, we're looking in the ballpark of nearly 400 nights. Notice that CFHT is notably faster than dark energy camera for this work in the blue, just because of the superb blue efficiency and sensitivity of CFHT. It's doing something that LSST is not doing. This is a different kind of imaging that is opening up different space and different science. So it's not just adding a northern component to LSST. And I'm envisioning this as a bit of a Unions-like multi-telescope effort where we're using the strengths of a CFHT and dark energy camera and hypersuprime cam together. And basically, because of this, imaging would be critical for DESI-2 high redshift target selection. That would be highly valued by the DESI collaboration, and as a result could be used to buy in like of order kind of 15 plus 15 French and Canadian DESI-2 participants. That's all, those numbers are of course just matters of negotiation and so on, but that's sort of the ballpark just to give you a sense. So I just wanted to kind of briefly show a couple of these, bits of what this imaging is useful for. So as I said, they're great for low redshift photoses. So this sort of opens up a lot of dwarf galaxy science, because as I understand it, for a lot of, if you want to study dwarf galaxies with lensing, the limitation is not measuring the shapes of the galaxies behind the lenses. It's actually getting photoses of the lenses. So in this plot, the redshift limits here are 0.4, and this is showing photometric redshifts with hypersuprime cam imaging versus hypersuprime cam plus our new DCAM IBIS imaging. And you can see that it basically just cleans up that locus like an incredible amount. Perfect, 3 minutes, thank you. And then there's a related plot going out to redshifts of 1.5. And this is now showing Cosmos 30-band photometry versus IBIS. And you can see that it's pretty competitive. So it really does a pretty fantastic job for cleaning up photometric redshifts. We've talked a lot about DESI spectra. So this plot shows some 7,500 DESI spectra. So in this image, and this is showing essentially this big line is the Lyman alpha line for a bunch of galaxies of redshifts about 2 up to 3 or so from our little pilot survey taking a couple of nights. And there are lots of fun things to look at. In this image, you can see these are the filters they were selected from, and you get a bunch of galaxies kind of uniformly spread across the band, and then a little kink at the edges sort of mapping out exactly how the filters overlap. And one of the nice things from this sample is that actually just the photometry, because you basically get coarse redshift information, just the photometric samples are really valuable for doing cosmological cross-correlation samples. So for example, you can do CMB lensing tomography just with the photometric sample. So I think there's there's a lot of value just generally in this imaging data set. Perfect, 1 minute. All right, so back to the kind of summary slide. I'll wrap up 45 seconds early. Thank you.
Thank you. So, questions?
Sorry, I keep ask questions. So there's a slide you show that the comparison of the DCAM nights and CFH nights, and you say that CFH takes less than DCAM. One is 99-ish, one is 130-ish, but you're counting those as 10 hours per night. But CFHT megacam, if I recall correctly, it's 5 hours per night. So that means that it requires 180 nights instead of 90 nights. But is DCAM really doing 10 hours per night? Because if that's the case, then CFH is not winning even the bluest band. So can you comment on that in terms of overhead? Is that I don't know. I mean, I should probably know what's the overhead of CFHT megacam versus the megacam. Is really the overhead causing the 5 hour versus 10 hour difference? But it would be good to actually put in at the fair amount, including the overhead, and see which one is more efficient.
Yeah, I think I included in that, that was very much a course estimate. So it includes readout of cameras and things, but not weather. So, obviously the 10 to 5 hour accuracy of Chi, just a pretty, fair fraction of that is a weather cut, I would imagine.
Hey, Dustin, yeah, can you comment on how on earth you get 10 hours per night on day cam?
Sorry, what was the question?
It's 10 hours per night, right? In terms of scaling for surveys. Now, where's that number coming from? Because the night is only 10 hours, right? So you get no bad weather, no...
Right, exactly. In those projections, there's no bad weather.
Uh-huh.
It's one number it's using, but also for that and I get 5 hours per night and whether some quality of thoughts for get hacker.
Of all the numbers that I thought would cause trouble, I didn't think that was the one. 3 times bigger field as you, but seeing statistics obviously much better on CFHT. So that helps a great deal as well.
So you mentioned that your bluest filter is very close on the calcium plus CH and K of Starkenberg and Martin. Is it the same filter or it's something different? I mean, it's slightly different design. I mean, can that science be done using that filter over the
I think unfortunately it can't be done because so the calcium H and K goes from about 3,900 to 4,000 angstroms, and our bluest filter starts at 4,000 angstroms, so it just like directly butts up against. So you don't get those calcium lines in our bluest band, but you do get a lot of other metals going on.
Yeah. The obvious follow-up is, has anybody actually looked at quantitatively the sorts of stellar parameters, etc., you can extract using those filters, or is that analysis still TBD?
Sergei Koptysov has taken a look at them. I didn't have time to consolidate and figure out those plots. But yeah, I think, so as I understood it, log G was sort of the best. They were really good for.
Thank you. So we'll stop here because otherwise we have so other talks. Thank you.